It started to leave. So I've been speaking a long time on big picture topics. In the last 10 conferences, the topic has come up, what do you guys do for a living? And I hope that's of interest to you. May I ask, can I do some data science? Is that okay? Yeah. Help me out. How do you come to this? Are you trained as mathematicians by show of hands? Physicists, chemical physicists, engineers? A few, okay. Life sciences, computational biology, genomics, gotcha, okay. Financial mathematics, gotcha, fin math, that's my background. I was a bond quant for a very long time. We're in the house that Goldman Sachs built here, by the way. Quantitative business methods, how about life sciences? How about, let's see, what else is there? Social sciences with heavy stats. Okay, and how about IT? Math isn't your thing. Okay, let me get through this thing then, and then maybe I see about 100 resumes a week, and so maybe I can help you with your job search if the physics isn't interesting. So I was just in Stanford, and I was reminded that applied statistics, data science is just applied statistics in San Francisco. But for this talk, I'm going to define it to be statistical mechanics, okay? And go through an industrial problem. So the idea is you've got a network operations call center here. There's a failure, there's a mean time to detect it, isolate it, restore it. Restore doesn't mean repair. Restore means fail over, right? And then your call center lights up, and they're telling you something you already know. Your video is down. And by the way, all the action is in video. It's not in internet, and it depends on what's happening. Like if Angela Merkel or Trump or Obama are saying something, nobody cares, right? If the video goes down for 5 seconds. But if Tom Brady is going like this and the video goes down for 5 seconds, all heck breaks loose. So it kind of depends. And then you fix it when you can, and it's just kind of compelling to want to get out in front of this problem. So if you can predict that, then you obviate this. Your ROI is the call center. And then if you can take any unplanned maintenance workflow and convert it to planned maintenance workflow, you win the gold stars, and sometimes you get to send a bill for a couple bars of gold bullion. So how you do deep, there's a satellite dish missing here, but how you do deep packet inspection on PIMI, GMP, multicast video things. If you happen to have a team of brilliant electrical engineers around like some of you, then it's simple. But what you do is you listen to a few channels. That's 50 megabits a second. So this storyline goes for any telemetry, for any sensor, anywhere, including telematics, like the good professor here a few moments ago. So if this problem domain doesn't turn you on, this mathematics is of interest to any problem domain where there's streaming data. But 50 megabits a second, we had 4 of those, and 2 failovers, though. So 300 megabits a second. You've got a good system clock. So here's how it works. You divide time up into 1 second intervals or any other time that makes sense. And I like powers of 2, you'll see why. So 128 of those sliding time windows is an eon, an epoch rather. An epoch, you do some calculation. That looks like a Little League football playbook, but it's supposed to be a support vector machine. And you do some scoring, and then you got precision, recall, sensitivity, all that stuff we tell our bosses we understand. So, of course, when I switched up on you, there's a log regression, but when you do that, you need a labeled data set, and you can't label a data set at line rate. I mean, at U of Chicago, you would just give it to a graduate student, right? Here's 5 petabytes, mark it up for me, chapter 12 of your dissertation. It would kill the graduate student, but we don't care. We have more of those. This is the U of Chicago, so that kind of thing. But you don't have one of those. Do you remember the Lila Lucy thing with the bonbons? And she's eating the bonbons and the bonbons. This is the bonbons. And you wonder, has anybody ever solved for the bonbons? And it was Walter Shewart, and he was standing very near the corner of Cermak Road and Cicero in Hawthorne, Illinois. That's now part of the incorporated Cicero at Western Electric Bell Telephone Laboratories, it was later. And he kind of solved this, especially for those kinds of devices there that were integral to the telephony network. And what he said is, when a gremlin gets in this system, when some kind of an anomaly gets in a system, whatever it is, widgets off the conveyor belt or packet streams, that what happened is this thing skewed left. So all of the probability density is on the right, or maybe probability density pushed itself out to the tails. And I'll just ask you to kind of commit this to memory. My goal here is to take this and move it forward about 20 time steps. There was a question earlier in the morning, how does data analysis and data science, what's the deal? And I don't know, I don't have a definitive definition, but at least in my shop, data science is prediction. And data analysis is maybe the past tense that happened, or maybe the present progressive tense, this is happening, oh my gosh. But prediction is what we do for a living. So we want to move that out as far as we can. So just kind of memorize that and maybe think of that as a bar chart if you could, and what that would look like. And since we are in Chicago, I just thought I'd mention that this whole problem domain here came from Robert Millikan's lab. These guys especially did the oil drop experiment that won him a Nobel. And then, so that's kind of 1907 to kind of 1917. So this is 100 years ago. It's kind of a timeline along the bottom. That's Lee DeForest. They met him at Drexel, and got this. Lee DeForest knew how to make a diode to triode, and he did that for wireless communication, but these guys wanted it for wireline communication. And the thing is that was not an evacuated bulb, and so the gain across that was kind of retarded by Brownian motion effects, and these guys were experts in that. They discovered Brownian motion again during the oil drop experiment. This is what it takes to evacuate that bulb. It was extremely expensive to do. There's the most important and highly paid professionals at the corner of Cicero and Cermak. Those are journeyman and master glass blowers. And when they got that device made, it had a mean time to failure of 1,000 hours. They needed them all over the world. But with that thing, you could speak from, say, New York to Perth, Australia, and that sound would be as clear as mine is now. Before that, they were kind of impeded at the Front Range around Denver. They couldn't get it from New York to San Francisco. These two guys, Mervyn Kelly, he took his PhD down at Hyde Park. Clinton Davidson was an undergrad there, and they went to Princeton directly to join the faculty. You might have heard of him, the Davis-Germer experiment that proved Louis de Broglie's theory of matter waves. When these guys were done with this process, the mean time to failure of that 101D repeater tube was 80,000 hours, about 10 years. There it is now. If there are any bass guitarists in the room or audiophiles, I'll bet you've got a few of those at home. Data science is cool. It's just not that cool. So here it is. Now, so what's the deal with 1931? Between 1930 and 1935, Western Electric Bell Labs lost 85% of its workforce. So they had to get smarter and get better really fast. So Walter Sheward kind of tried to figure out how to optimize productivity. If there are any industrial engineers in the room, I'll bet you've had this course. They still give the Sheward Award to the Reliability Society every year. Well, there was a World War. There was a Great Depression and a World War. And then when everything returned to prosperity, they started to think about this again. E.S. Page at Durham and later Cambridge, Cavendish Labs, started to think about continuous sums. Is there some continuous mathematical thing we can watch so that we're immediately alerted that there's a gremlin in the system, that an anomaly, say the car is going to turn the wrong way or something, or there's going to be a failure in the packet stream. Roberts was at Bell Labs in New Jersey. Anytime you add things together, it's just compelling to multiply them together. So he started to think about geometric moving averages. And Shuryev was at Moscow State and later Manchester, a student of Kolmogorov, who I'll bring up in a few minutes. He thought about exponentially weighted moving averages. I'm a retired bond quant, so I kind of did this throughout my 20s, 30s, and 40s after graduate school. And boy, was I surprised, because George Moustakidis at Patras in Greece, at that time he was at Drexel, he went up the street to be a Princeton Tiger for his dissertation. He showed that even for the Ito calculus, even for bond prices, everything we do in this building, Page was right all the time. So I don't know if I wasted time or invested it, but Moustakidis showed that E.S. Page was right all the time. So here's what Page is saying. He's saying, look, Sheward, I don't know if this bell curve skews or if he's pushing density out to the fat tails. I think what's happening is the gremlin is moving the mean time to failure. So 7/2, that's 1/30. So that's a monthly defect. And he added 23/2 and to increase the mean time, to lessen the mean time to failure. And so that would be 7/20, that's 1/7. So what used to be a monthly defect is now a weekly defect. That's what I think is going on. And if there are any data scientists in the room, you've been through the logistic regression formulation, you'd be very comfortable in this paper. That's what he did. It's a log likelihood argument. And he plays a little math game, and he asks, how can you know, and when can you know, and with what quality can you know? And so what he says is, let's say if we start at a baseline, you're sampling normal random deviates from here, and you'll go down here, and when there's a minimum, if the gremlin moves that up there, then that's going to realize as Short's drift. That's Short's graph, isn't it? Through completely different physics. And so what he's saying is, if you were at a minimum, then you had a change point. The car's about to turn the wrong way, or the telemetry is corrupted, or the data screen inside the network operations center is jittery. And you know, there's 45,000 people working in Cicero, so you can't just send two shifts of people home. And so you have to have a threshold, just like we data scientists do today. You know, you have to be sure. And just because you have a minimum, so if you have a minimum, you had a change point. But I myself put this change point in here. I put the gremlin into time step 21. This is an eon of 100 sliding time windows of 10,000 random deviates. And I myself changed mu right there. And you can see that only 25% of the time do I get pages graphic. The rest of the time I have to rely on Short. So Page didn't kick Short out of the nest. Short's still required. There we're drifting, even though the change point was not a minimum. Okay, so we know how to get signals and tally them up. So what signals? This is what telemetry from a network operations center looks like, or the professor's car, or any other problem we've had today. It's kind of a mess, and you can see here it goes to ground. So what you're seeing is an eon of 128 sliding time windows, and this one went to ground. These are not sequential. I just grabbed these out of the nest. 39 was what caused this problem. I got very excited about that because they're not easy to find. Anybody who's done, you know, physics research or engineering research in graduate school, you know, finding data is hard. You know, in school they give you the data, but I mean in school in grad school you've got to go manufacture the data and catch it. And so when we actually caught this thing and we had a gremlin in there, we were very excited. Let me talk you through it. So you've got 1 second sliding time windows, 128 of them. So this is just telemetry or telematics or packet streams or anything like that. You've got a moving average there, and then you've just got this time series, or this series of time. It's actually not a time series. Remember, a time series has a constant mu, and it has a variance that is only a function of the time step. Right? And that's not that. And I think you can tell it's not that. That is not equal to that, and that's not equal to that. But what was key is the network engineers told us that it was in the same state. How can that be? I mean, it's clearly not in the same state, and they absolutely, said that it was in the same state. Well, if that's the case, then let's get out of this time domain and go to this frequency domain. There it is, using this kind of Fourier transform thing. So there it is. So this is that in a different representation. But can you see the blue dots are moving around too? So that didn't answer the question. So what we did is we took some inspiration from, kind of the particle physics guys down in Hyde Park. What they would do is renormalize this. And so if you do that, you get this kind of representation here. And look at that. In this representation, they are indeed in the same state. Pretty cool trick. Except for epoch 39, which is obviously a gremlin. It turns out that's about a 5.5 sigma anomaly. So I mean, if you hit this thing in your car in the network operations center, you're going off the roof. This is not good. And in fact, it was a serious failure in the network that evening that caused a huge remedy ticket and things like that. So there is a lot of money on the table to try to solve this problem. Well, one thing you can do, remember this little trick? Did you learn this in school? If you take this little guy and you make a cumulative distribution function out of him and compare him to the cumulative distribution of the normal distribution, the absolute maximum difference, and that could happen anywhere, could be there, there is a test statistic. Remember your z-test and your t-test and your chi-squared test and your f-test that you said you'd never use again? Well, that's the Kolmogorov-Smirnov test, the Ks statistic. And if you plot that, remember I asked you to consider Shuryev's graph as maybe a bar chart, you get this. So I'm plotting the Ks statistic for each one of these little guys as they arrive. And it looked like it was normal. And in fact, it turns out if the person working on this project had done a better literature search, we would have discovered that, because E.S. Page himself and it was me that did the literature search, by the way, but E.S. Page in 1954 actually knew this. And what he said is when you have a vector representation like this, remember the natural language process fellow 2 talks ago was talking about vectorizing the speech? When you have a vector representation here, the internal angle, these would be very small, but you could do a bootstrap aggregation on these things. And the internal angle here is a test statistic, just like the z-test and the t-test and the chi-squared test and the f-test and the ks test. So, and he actually published critical values for normal distribution, Poisson distribution, exponential distribution, Weevil, several of those things. And so if that's true, if that is normally distributed, and we thought it was anyway, but if that is normally distributed, we can set critical values, and there's, I'm going to talk to this now, that's the bar chart representation of Shewhart's graph from the first couple slides. Then we can borrow some inspiration here from the particle physicists and create this kind of annihilation creation algebra. So what's going to happen is if these guys are well behaved and they're there, I'm going to deflate this running continuous total with a factor, say 0.9. So it's going to go down. But if that little gremlin even peeks up over there and gets right here, I'm going to whack him with a really big multiplicative factor. And the reason that's predicted is, can you see this jitter kind of comes here before the crazy failure here? And you know that from driving, don't you? You get out of, you get into a resonance, and you're going to lose control of the car, whether it's a human driver or an autonomous driver. And so you kind of know this from your behavior, but it makes sense that you can see that in telemetry or telematic packet streams. And so what you get is something that looks like this. Now that, remember, is Shewhart's graph, but instead of being here, it's 22 full eon. That's not. That's 12. However, can you see that I've quashed the scale here? This thing lifts off the baseline 22 full eons. 128 seconds times 22 in front of the actual anomaly. Well, that's in a problem domain where 3 minutes is actionable, and if they have 5 minutes, they'll stop and get a cup of coffee on their way to fix it. So that this was a huge deal, 7 full generations. And what that lets me do is, oh, by the way, the data analyst would say there it was. Shewhart at 31 would have said there it was. What this lets you do is say, here it comes. That's what this is all about, to try to get out in front of the problem. And what really helps us is this annihilation creation algebra that we took from the particle physics course. So now I have a labeled data set, finally. So this stuff is streaming by. The bonbons are just streaming by, and I'm able to make a labeled data set as they come and go. And with that, I can undertake all the standard machine learning on that most people in this room have had. That's the recipe. I'll put that on my Git or on LinkedIn or something. But I think that, I wanted to emphasize really that what is old is new. Nothing that's been discussed today is new mathematics, or new physics for that matter. But it is a very new application of some very sexy stuff. But I'm asked often, what can I do to get in this field? And my best advice, in all honesty, is study your maths, study your physics, and get your mind around how that stuff works, and read as much as you can. And you'll find a lot of those papers are not the newest things out there. So with that, I'll close, and I'm pleased to take your questions. Sure. Yes?
Well, thank you. That was a very interesting talk from me. Look, what you guys have an issue there is I have an issue for apageneticists. Look, sometimes when you have like a gene of a small effect, that gene actually inflates the value. So just to make sure, you guys have an eon, right? What is an eon? Is like a package of signals, or?
An eon is a data construct of 100 of the packet statistics for 128 seconds of data.
Okay, so what you said basically, by looking at the data, using this physical approach, physicization approach, using like a multivariate, using the normal statistics, you'll be able to evaluate those like stream observations, right?
Right.
And then since they're inflated, because that will actually cause your prediction, they inflate your predictions, you kind of inflate that a little bit, right? That's kind of, if I understood correctly.
The annihilation and creation algebra you're speaking of?
I know, mathematician.
That little trick that I use to whack them? Yeah. It's an amplifier. It's a mathematical amplifier.
Okay.
And so if you know the character signature of an anomaly, then you amplify it by some number that makes sense to your problem.
Do you guys care about buffer running correction, or that doesn't affect you at all?
Sure. Yeah.
Okay. Thank you.
Yeah. Yeah. Yes, sir.
Can I ask a theoretical question?
Please.
In all these signals, can you apply more variable meanings to it so that in one packet there's different dimensions to stored encode information?
Those packets, so PEM IGMP multicast video packets, in this case, have a very verbose header. And the payload is worse. And a lot of, so I think the answer is yes. Am I being responsive to you?
Yes, but how?
Might go back in time at this guy. Maybe not. Ask me a different way. See if I can do better.
I'll ask you later.
Well, let me repeat it. Your question was,
It's a little weird.
okay.
I'll ask you later.
Okay. I should have, yes, sir.
So let me get this right. You use an algorithmic approach to figure out a way of labeling the data.
Yeah, the question is, so we're using an algorithmic approach to label the data, and that was our main problem.
And
No
then you
labels.
use that to train
To further train models, which wasn't discussed here.
So that begs the question: why don't you just use your algorithmic approach in the first place on live data
Yeah.
for classification?
And that is a product with which we do. So he asked, if you got this far, what's with the further machine learning? Aren't you done? I'm paraphrasing. This is a product right now for workplace safety, workplace telematics, and machine interface, proactive energy usage, huge industrial batteries that are charged when the coal or the uranium is expensive, and you charge up the batteries and you discharge the batteries when the coal or uranium is cheap. It's when it's in the middle you have to make a decision. Also in the middle of that, I'm not a manufacturing expert, I'm sure we have some here, but it turns out that irrespective of the cost of the job, you run against deadlines. And so the shop floor foreman will say, listen, we have to get 200 Toyotas to Nashville tomorrow, so just do it. But boss, it costs a lot of money. We're out of time, we gotta go. So that's where the traditional machine learning comes. And until we know how to label streams, we can't run those machine learning algorithms on the streams. Yep. So data, may I ask just by show of hands, how many deal with data at rest in general, and as opposed to data in motion? Oh, and a lot of people are not. Okay. I am out of time, and I'll be around for some conversation, but thank you for your attention. I appreciate it.